Should be fine now. Yes? Okay, so I will be talking about maybe a slightly unusual topic, but I hope that what you saw earlier today in the other talks in the session will be helpful for this. But yeah, usually when you think about mathematics and machine learning, you think about using mathematics to sort of improve machine learning or sort of understand it a bit better. What I'm going to be interested in for the purposes of this talk is understanding if machine learning can play any role in mathematical research. Yeah, and this is a very broad question, of course. So I've sort of roughly structured it into like 3 parts, which I would sort of say are 3 views of what how you could describe what's going on in machine learning and sort of how you can use these properties for your mathematical research. And then at the end, I will give sort of some concluding remarks on like what you should look out for when you try to sort of apply any of these things. So the first property that I want to talk about is approximation. And you've seen plenty of times now how a neural network is defined. So let me go through this very quickly. Of course, if you have a matrix and some vector, and you use this to define a map, as we can see there, then this is just an affine linear map. Or in terms of machine learning, it's a single layer with a bias term, the B. And of course, this just describes a single line or a hyperplane if you're in higher dimensional space. And if you have a bunch of points and you see think for some reason that they can be well approximated by a line, then you can do this. This is linear regression, and you're very happy. If you have points that are sort of structured more complex than what we see there, you might have the idea of sort of stacking multiple of these affine linear maps after one each other. If you just do this, you're just going to get another affine linear map, so this is pointless. But if you now use some function g to introduce some form of nonlinearity, then you can actually start to get very interesting things. For example, if your map g is what we have already seen, the ReLU function, then you actually get piecewise linear functions, yeah? And then you can sort of start to believe that since you have a piecewise linear function, you can approximate your data pretty well. This is called a multi-layer perceptron. So what's actually a neural network? I would define a neural network as just a multi-layer perceptron that takes the input data into consideration a bit more, yeah? So the most obvious case of this is something like a convolutional neural network, which we see here. So this actually goes back to, I think, 1989, but didn't really become sort of prominent until 2012 when AlexNet sort of dominated the ImageNet benchmark. And what you're doing here is you're just saying, well, I don't just want to take my input, which is an image, and just like make a huge vector out of it. I want to use the sort of topology of the problem. And presumably adjacent pixels are relevant for a pixel. So why don't we bake this into the neural network? And this is precisely what you do in convolutional neural networks, right? Then you can do this with similar structures. For graphs, this is very popular, right? If you have a connection between 2 vertices, then this probably means that you should take these into account. So you can sort of pass information along edges. And then more recently, as people started looking at sort of large, at language processing, people developed these attention mechanisms, which turned into transformers, and this is sort of starting to be the dominant kind of neural network. We already saw on the previous slide that if you do this, you can sort of get an idea that if you add enough breaking points into your function, you can sort of approximate your data very well. And we, in fact, have a statement that says exactly this. This is the universal approximation theorem. I think this has been stated. It's a very old result. It's been stated in many different ways by many different people, so I'm not attributing it to anyone. But basically, it just says that any continuous function with compact support can be approximated arbitrarily close by a 2-layer perceptron, right? So 2 layers are enough. And then if you make them just big enough, i.e. wide enough, and in this case, we're assuming we're using a ReLU activation, then you can approximate your data as closely as you want. Of course, if you don't want to make it super wide, you can also consider what happens if you sort of restrict how wide you can make them. And then people have studied this. And then, of course, you need to go deeper, but there's sort of a trade-off between how wide and how deep your network is and how effectively you can sort of model things This is, of course, a sort of analytic or numerical statement, right? You're sort of getting within an epsilon bound of your function. You can also ask sort of exact representation, and just want to highlight one sort of one line of research, right? You can ask how few layers can you use to exactly model a specific function. For example, the maximum of the input. And I'm just highlighting this because this was done by Christoph Hertrich while he was a PhD student here in Berlin. So the question is, can we use this universal approximation theorem or this property? And I want to sort of demonstrate that you can for a particular set of problems in mathematics, which are problems where the answer is given by a kind of concrete object. Yeah, so there are some questions in mathematics where if you can just give a concrete combinatorial object or geometric object or anything like this, then everyone will immediately believe you. For example, sphere packing. What is the densest arrangement of congruent spheres in Euclidean space? Very tough problem. But giving an upper bound, or sorry, a lower bound can be easily done by just explicitly describing such a packing. So this is kind of like a very concrete object. There's also the Hartwig-Nelson problem. If you color the plane so that no 2 points at unit distance get the same color, how many colors do you need? You can just give a particular coloring, and then people can look at it and sort of verify it and believe you. There's a lot of problems in graph theory that are of this flavor. For example, Mantle's theorem, what is the maximum edge density of a graph without triangles? And you might say, well, this is sort of like one particular graph for one particular size. Doesn't quite fit this because you would need like a sequence of graphs. But there's a whole theory that sort of describes sequences of graphs as graphons, or you can just describe it as the blow up of an edge. So in a way, it's also one particular object. So the question is, or the idea is, can we somehow get a neural network to represent these objects, right? If we can somehow get a neural network to give us these objects or just directly represent them, then this would be very good. And the first paper that I should mention in this context is by Adam Wagner, back from 2021. And he did his PhD in extreme combinatorics, and I know him because I also did a PhD in extreme combinatorics. And he was very into using computers to sort of answer questions. So before this, he also had a paper where he just sort of showed people you can actually just use an ILP solver to answer many questions, right? And he sort of had this idea of using neural networks and sort of reinforcement learning to sort of approach these problems. And this sort of got a lot of attention. So Timothy Gowers noted it. Tao invited him to a conference to talk about this paper. And then he also got a Quanta article. So he definitely got a lot of attention for this paper. So let's sort of look at how the method actually works that he describes. So he's interested in combinatorial objects. So let's say graphs for the purposes of this example. And you can represent them as binary vectors, right? So you can take, for example, this graph here as an edge, edge, non-edge, or in the order edge, non-edge, edge, which corresponds to 1, 0, 1. Yeah? So now you could ask, okay, I'm playing a game. I use whatever people do for, let's say, AlphaZero or any kind of like neural network-based chess strategy. And I sort of consider filling in these ones and zeros as rounds. So you ask in the first round, what digit do you want to put here? You put a 1. What digit do you want to put here? You put a 0. And at the end, you get a full state. And then for reinforcement learning to work, you kind of need to give it some feedback about what's good and what's not good. And the way that he simply did it is he had a very clearly defined cost function or loss function that he wanted to optimize. He just chose the best states, disregarded the others, and then sort of reinforced them by just putting them in the training data set. Yeah, and this is the kind of basic idea behind what he did. And I'll make a bit of a comment because we have a combinatorial optimization crowd, so many people might be having questions right now, and I'll comment on this a bit later, but I think my microphone's, hold on. Let's see if it sticks now. Yeah, so this was the basic idea behind this approach. And the results that he studied, for example, he looked at a conjecture that said any connected graph on n vertices with a certain matching number and largest eigenvalue must satisfy a specific inequality. And he sort of ran it, and I think this is on 17 vertices. He came up with a counterexample. Yeah. Similarly, he studied this conjecture, which is about the graph diameter, proximity, and distance spectrum. And this, he didn't get an explicit counterexample, but he got something that he could generalize, right? Because this has 190 vertices, or a bit more than this, which is too large for him to optimize over, but he was able to look at it and be like, okay, probably if I just add a bunch of vertices here, this works out. And then finally, he also studied a sort of 0-1 matrix problem where he was looking at the permanent and what's the largest permanent that you can get if you avoid certain patterns. And he came up with this like very interesting sort of pattern that started to emerge, and also a counterexample to the conjecture. Okay, so this is not the only paper that sort of works in this direction, right? And you can see that in a way, it is using this universal approximation of neural networks to sort of model these functions. It's in a kind of convoluted way, because you're sort of putting it in this reinforcement learning context. So in a way, your neural network is defined by the sequential execution, and then sort of the whole thing together is kind of modeling your distribution, but it kind of sort of fits in this context. Another result was that you might have seen was about faster matrix multiplication algorithms. And they, in the end, actually used a very, very similar approach. And you might be wondering how this is possible, how sort of kind of like reinforcement learning, essentially discrete optimization approach, can come up with matrix multiplication algorithms. But it turns out that there is a well-known reformulation of matrix multiplication, where you're essentially trying to find a low-rank tensor decomposition of a three-dimensional tensor. Yeah, so the basic idea is, if you just write down the sort of obvious way that you would define matrix multiplication, even for a 2-by-2 matrix, you use a certain number of multiplications, and it turns out through surprisingly convoluted ways, you can sort of get to the same result using fewer multiplications. And this is precisely, if you write down just the sort of basic definition as this three-dimensional tensor, these like operations that use fewer multiplications is exactly this like lower rank decomposition. Yeah, so in this case, each round consists of finding one component of this low rank decomposition, and the feedback is, okay, either you didn't succeed and you were this far off from decomposing the matrix, or you did succeed and you needed this many rounds, i.e. this many components. Yeah, and then you're trying to minimize this as well. And they used, I should say, this is a lot of people from Google DeepMind, and you can see that previously we had one guy doing his PhD, and now we have quite a few more people. And of course, parts of them have also previously worked on AlphaZero, so they had access to like a lot of tools and machinery for this kind of problem. And of course, this also got a Quanta article. I want to highlight one more result in this section. So I'm not being very modest now, and I'm highlighting one of our own results that Sebastian and I did together with 2 PhD students in our group. And this goes back to this question of Hartwig-Nelson. How many colors do you need to color the plane so that no 2 points at unit distance get the same color? Yeah, and we already saw you can clearly do it with 7. Yep, so this uses 7 colors. This is just one of very, very many colorings. And the question is, can you do it with 6? And you can think about what is a coloring. A coloring kind of is just a mapping from 2 dimensions, yeah, you're in the Euclidean plane, to let's say, 6 colors that you have. Yeah, and this is very discrete, so we can turn this into something that is continuous by instead mapping to a probability distribution over colors, right? So you're mapping to the 6-dimensional probability simplex. And then you can sort of say, okay, this is a coloring, and now I want to basically model this using a neural network. Yeah, so you have a neural network that has 2 input neurons. Very simple structure, was just an MLP. There was some tweaking that we did with the activation function, but otherwise it just has 6 output logits, and then you throw a softmax on there, and then you get a probability distribution, and you sort of evaluate this as the coloring. And if you can switch to the video. So if you start with a randomly initialized neural network, and you sort of derive this coloring by just asking for every pixel that you see here, basically, okay, this X and this Y coordinate, what color do you get? You get, of course, you get a probability distribution. We're just argmax sampling here. And then what you can do is you can start sampling points at unit distance and measuring the probability that they get the same color. And this is all continuous and differentiable. So you can just take a gradient and run gradient descent. Yeah, so you just sample 1,000 points at unit distance. You calculate the probability that each of them are monochromatic. You do this in PyTorch, all differentiable, and then you just say, take a small step and adjust the neural network so that hopefully it avoids this. So can you press play? This is what you will see now. This is the training process. Okay, so you can see that very quickly. I should also mention that I put sort of lock on the time axis, right? So it will actually sort of converge much more quickly to this kind of pattern, but to sort of show the initial phase a bit more, which is interesting. Yeah, you can see that it very quickly to converge is something that looks quite interesting. First of all, this is not, unlike some of the other examples that you saw previously, where the output is already the finished product. This is very much just intended as inspiration, right? So you need to look at this and think about what you're seeing and does it actually work? So let's sort of think about this. It overall looks pretty good, right? So it's like clearly this like pentagonal shape, and it's just the same shape repeated. But you see that when you check how to avoid sort of points at unit distance that both get the same color here, while also making sure that this isn't too large so that you're not getting a contradiction here, then you do eventually run into a problem. Can you switch back to the slides? And this is actually something that other people had previously already noted, which is that you can almost color the plane with 6 colors. And almost means really up to a minuscule part of a percentage point, right? So you need to take sort of out like tiny bits here at this site. This was done in, I think this was like 97 or something. And then this was quite recently, someone sort of improved the like calculation of like exactly how large these need to be, right? But this is like minuscule changes. But otherwise, overall, it's pretty much the same coloring that the neural network found, which is good. It worked, but also means it's not a new result, right? So what we instead did is we looked at kind of an off-diagonal variant of this problem that had been studied previously, where you just say in the 6 color, you're looking at different distances that you want to avoid. And these are sort of the 2 colorings that we came up with, right? So this is the final formalized version. And I personally think these are quite neat. They're quite nice looking. And it's also, at least I could not have come up with this without like having the inspiration from a computer sort of giving me a picture that looks very similar to this that I can then sit down with a pen and paper and sort of check if the trigonometry works out. All right, so this was the first part. When did I start? 35. Okay, good. It's the first perspective. Let's look at generalization. So what I just sort of demonstrated is perhaps not what you think of immediately when you think of like neural networks and machine learning. What you like more commonly might think about is these kind of like classification tasks where you like have some pictures of dogs and cats. You model this in this like very high dimensional space, and you have this magical function that tells you whether or not the picture is a cat or a dog, right? And if we think of the universal approximation theorem, then this just tells us that no matter what the data set is, it will work if the network is large enough. Yeah. So on your training data set, the fact that you can get the loss to go to 0 is not surprising, because we have the theorem that tells us just make your neural network complicated enough and it will be able to represent it. Okay. Minor details, you're using gradient descent, right? It's not like exact optimization, but ignoring this. Basically, universal approximation tells you that on the training data set, it will work. But if you have ever done anything with machine learning, you know that you shouldn't go by what you see on the training data set. You should sort of have a separate evaluation data set, then maybe tune some parameters on, and then only when you finally write everything up, you should go to the test data set, and you should report those values, right? Because that's the actually relevant values. And what's going on there is what we call generalization, right? So for some reason, your neural network has some kind of bias that even though it could represent kind of any input data set, and therefore also kind of represent this particular input data set in a way that doesn't generalize at all, the way that we sort of ended up training neural networks sort of tends to generalize very well. Yeah. And I'm very grossly oversimplifying now, and I'm very sorry to anyone who works in the field, but sort of the way that I think about this is that classical statistics emphasizes very simple models and guarantees, right? So you have like very clear assumptions, very simple and very well understood models. And you can make very sort of clear, you can say very clear things about what you would expect and why the output is the way it is, given that your assumptions are correct. And in sort of big data, which this field is essentially, you sort of just say, screw it, we're going to use a very over-parameterized approach. We're going to use insane amounts of data, and we are not going to give you any guarantees. We're just going to sort of accept the way it is, everything the way it is. We're just going to run experiments, and then hopefully, if we have a test data set and it performs well on the test data set, that means it actually works. Yeah, and also implicitly, you're accepting things like adversarial examples, right? I think this basically has not been solved. It's just sort of an inherent thing in neural networks. There are some ways to mitigate it. I don't think in practice, probably people care that much, because usually you don't have direct access the way that you would need for these adversarial attacks to be efficient. But this is just sort of something that we kind of understand, but can't fully explain, and we just accept it because it works in practice. Yeah, so in the past, this has been sort of like described as alchemy. It's not really like the hardest of science. It's definitely not like pure mathematics. The more favorable way of describing this, I would say, is that it's ultimately an experimental science, right? So you will always need to sort of supply some experiments that you ran, right? If you want to convince someone of, hey, if this machine learning approach, it works very well, the way you will convince them is definitely you include data and tests, and you have like a very sort of clear test setup. Okay, good. So same question as before. Can we use this kind of generalization to our advantage when we're interested in mathematical research? And there's one particular paper that I want to highlight, which is by a bunch of engineers at Google, or DeepMind at the time, I think. Yeah, it was still DeepMind, was still SEP. Yeah, at Google's DeepMind, with two different groups of people. One was Andras Juhas and Mark Leckenby, who sort of are, for the purposes of this paper, experts in knot theory, and Jordi Williamson, who is well known in representation theory. And I will focus on the knot theory part because I think A, this is the thing that was sort of more impressive in terms of the result, and B, I have a slightly better understanding of this than I have of representation theory, even though I'm still not very knowledgeable about knot theory. This is the mandatory Quantub article on this paper. So what did they do? Basically, just very, very basically describe this as a knot, right? It is an embedding of the circle in three-dimensional space, and they're equivalent, two knots are equivalent if you can continuously form one into each other. And then you can describe invariants, which are just functions that are invariant under equivalence, right? So they're basically defined under the equivalence classes. Yeah, and you can sort of exhaustively enumerate these. So you can say how many there are and exactly which ones there are. And this is sort of describing the first, what is this, 15 knots, like the 15 smallest knots by some measure. Yeah, and as I said, I don't really know that much about knot theory, but for me, it's very similar to how people approach graph theory, right? So you can also write down the simplest graphs. You also have invariants, yeah, certain graph properties, and you're interested in relating these graph properties, right? Now, Juhas and Leckenby believed that there was a very important but yet undiscovered relation between geometric and algebraic varieties. Varieties, invariants, I should say. What this means is that there's basically sort of two different sets of varieties that people studied. There's the geometric kind over here, and there's the algebraic one over here. And people had ways of relating them within each group, but they didn't really have a connection going from one to the other, right? So they kind of seemed like different worlds. And they conjectured very broadly that there should be some connection that people have not found yet. So what do you do? Well, you look at this and you say, I have these. Let's say I have determined all of these for my knots, and I want to know something about these over here. Let's say I want to sort of figure out the signature without running the explicit algorithm that determines the signature of a knot. Is there some kind of mapping that, knowing this information, can tell us with high confidence what the signature is, or even exactly? And then the idea is, why don't we train a neural network to do precisely this? Yeah, and this is exactly what they did. So they just generated a lot of data, determined all of these varieties, and then sort of tried to basically run statistics. They tried to use this information to predict information on that side, in particular the signature, and this is sort of the output that they had. And now I need to explain to you how this is derived, but this should not be news to you, because if you listen to the first talk, there are ways of figuring out sort of how you can attribute something in the output to the input, right? And this is basically the most simple version of this, where you essentially look at the gradient, right? So you're looking at, okay, it gives this output, and you can sort of attribute to the input input entries, you can sort of attribute an importance score that is basically just correlated to the gradient. Yeah. And what they sort of found is that the translation parameters for sure have the highest correlation in a sense. And then sort of it sort of quickly diminishes afterwards, right? And here you can also see the signature, which we're interested in, plotted over the translation. And you see that there's definitely some correlation happening. And based on this, they originally conjectured that this inequality should be true, right? So sigma is the signature. This is these two translations. And then for some reason, they also thought, based on their knowledge, that the volume should come in, even though the volume is very unimportant in this ranking, right? So you see this is also one of those cases where definitely it's not just the computer gives you the finalized proof or even the finalized statement. They definitely had to sort of use their decades of experience in the field to sort of interpret the data and make sense of it. This was the conjecture, and this conjecture turned out to be false. It was not true. So they found a counterexample, and then they went back and thought about it, and they refined the conjecture by including this term basically over here, right? So this should be the injectivity radius, which also doesn't have the highest correlation, but at least is somewhat up there on the list. And this they were able to prove. Yeah, again, the machine learning did not have anything to do with actually proving this. Two experts had to sit down and sort of try and understand why this would be true, and then they were able to do so, and this was a separate publication. But the inspiration very much came from neural networks and from sort of the idea that if they train it on a small set of knots, comparatively to all the knots there are, which is infinitely many, hopefully it will sort of learn something that generalizes, and that is they can then somehow interpret. All right. Shall I have? Yes, I have plenty of time. Good. Then let's get to the final part, which is sort of emergence, by which I just mean that even going beyond generalization, you see sort of phenomena that you could describe as emergence, in the sense that they sort of start becoming like bigger than the part of their sums, right? So everything that I've shown you up until now is kind of like, it's neat that it works. There was a lot of hardware sort of going into making this happen, but it's all sort of not very far out from what people were used to before. But all of a sudden, we start to have all of these systems that are sort of very different from what we are used to. So for example, I can just go online and ask the computer in human language to generate an image for me, and it will work, which no one's surprised by this now. If I had shown you this for like 2 years ago, everyone would have been amazed by this, but we've gotten used to it very quickly. Similarly, the way I code now, at least, is basically it's like 50-50. One side is code editor, and the other side is a chat interface with ChatGPT telling me what to do, because I can't be bothered to learn all the intricacies of every single programming language. And I mean, these are sort of just the very positive and kind of mundane examples. Of course, it also can go in a very different way. So I think the best image generation currently is not DALL-E 3. It's Flux, which I think is actually created in Freiburg. And it's very unrestricted, as it turns out, in what it will generate. And then Elon Musk, in his infinite wisdom, decided to incorporate this without any filters into Twitter. So you can get very interesting content now on Twitter. Right? Okay. But the question is, again, can we use this for something more sensible than generating pictures of Donald Trump? Can we use it for mathematics? And to some degree, it feels like we've seen less of this, right? There's not really been, even though we have this like magical black box that like spits out language and can write entire books and can write text much better than most of us can probably can. For some reason, if you've ever asked it any mathematical question, you will see that you can kind of very quickly go to a point where it returns gibberish. Yeah? So what's usually the explanation for this? Well, people usually say large language models are kind of like stochastic parrots. They just have sort of a very probabilistic view of language. And then basically they don't really have inherent understanding, reasoning, knowledge. It's just sort of all baked into this like probabilistic understanding of language. And it will just sort of return something, and it really doesn't care that much about if it's correct, because it just, again, it's just generating language. It's not about understanding anything, right? So there's this kind of like internal reasoning missing. And I would say this is actually, first of all, still pretty amazing. People usually use this to sort of denigrate it and say, well, okay, it's generating lots of text, but it's like pointless. I still think it's pretty impressive, because we used to be able to sort of think about computers as giving them very concrete input and very concrete instructions, and they give us a very concrete output. And now we can put something very fuzzy in, and this just comes at the cost of getting something very fuzzy out, right? So sort of just human language, in the same way that when a human tells you something, you sort of need to think about it, and you can't just be like, okay, perfect, done, this is acceptable, and move on. But I also think this story is not entirely true, and we sort of started to see some movements in this direction, because many of the big AI companies have started to think about math as kind of the proving ground to show that, in fact, their models are better than stochastic parrots. They can do something deeper. They can do some kind of reasoning, and the way they like to showcase this is using mathematics. So this is from a bit more than a year ago, from OpenAI, where they sort of talked about improving mathematical reasoning with their models. And I mean, a year ago is not very long ago in terms of normal research, but in terms of machine learning research, it is ages ago. It was in fact so long ago that OpenAI still used to publish stuff on archive, so you can actually read what their result was now. Now they won't do this anymore. But sort of many of these insights ended up going into their newest model, or I would say technique, because I think the model is really not the real novelty here, which is O1. And one of the things they used to highlight this is Math Olympiad questions, right? So they really like to tout that it's performing as well as a silver medalist, or in these kind of specific problems. Yeah, but if you've looked at how O1 works, I mean, they don't really sort of advertise this anymore, how it works. They just say it works. But you can sort of take an educated guess, which is that it's using this kind of like chain of thought approach, which really doesn't mean that you're changing much about the neural network or the training. You're just explicitly telling this finished neural network, okay, try to reason things through. Like the way you would tell a student who's not giving the correct answer, you'd say, okay, just sit down, think about it, sort of try to think about steps and try to reason it through. So basically, before it gives you an answer, there's this like whole internal thought process where hopefully it does something sensible. And then at the very end, you get the output back. And somewhat amazingly, this does actually work. So if you use O1 and you ask a mathematical question, it's still not going to be perfect, but it will make a lot more sense than just standard GPT-4 will. And in fact, so Terence Ho also thinks so. This was actually, you can't see it, but it was only like 5 days ago. I mean, this came out like, I don't know, a few weeks ago. And I think he might also have access to the proper model, which is not yet in public release, because he's very interested in this field. And so I wouldn't be surprised if OpenAI approached him. And he said that the experience is roughly on par with trying to advise a mediocre, but not completely incompetent grad student. Yeah, and previously he was of the opinion that it's a mediocre, completely incompetent grad student. I should also say, if Terence Ho says that you're not completely incompetent, you're already in the world's top 5% mathematicians for sure. OpenAI are not the only people working on this. There is also a lot of research going on from Google. So you might have seen this very recently, that they really sort of tout the Math Olympiad results, that they're sort of performing on silver medal level. And one component of this is was sort of already previously published and then sort of refined, which is approaching geometry questions. And another component, which again is not available in any written form, they will only give you like a blog post that's essentially trying to advertise what they're doing, but they're not giving you any scientific sort of background on this. But from what we understand is that basically they are trying to solve mathematical problems directly in formalized language, right? So when you give a mathematical proof in human readable language, you have the problem that it's kind of like really difficult. If you've ever like sit down and had to grade like an exam, and then you go like something is off about there, and then like actually pinpointing where the error is, like try to sort of doing this for the tons and tons of output that like this machine learning approach might generate, and then feeding this back, and then you get something that's slightly better, and then it's just a huge amount of like manpower that you would need to put into this. So instead, what people have started to do is using these kind of like formalized languages. So this is a whole other topic, so I'm not going to go into too much detail here. But basically, there's these formalized languages, which are essentially mathematics as code. Yeah, and if the code compiles, this means that your theorem was correct. Yeah, so it looks something like this. I think, yeah, this is Isabel. And this, of course, has the benefit that you can very easily give a computer feedback over whether it's doing right now is working or it's not working, right? It's just basically, did the code compile or did it not compile? And then you can sort of do many different kinds of approaches, reinforcement learning, supervised training. There's a lot of different things going on. And again, we're not really getting that much details at this point, but I would not be surprised if we're very quickly getting to the point where you ask ChatGPT something and it will actually give you a very sensible level on par with like a university student, right? So we're already getting to a point where if you just give it your standard like bachelor's degree exam question, it will probably do a pretty good job of answering them. Okay, so let me just conclude by giving you some pointers for your own research if you're interested in this field. First of all, I would say that implementing a machine learning approach is very hard for entirely different reasons than mathematics is hard. So this really depends. Usually I would give this to a more pure mathematics focused audience, which have absolutely no idea about what it means to code. You're all interested in combinatorial optimization, so you should have a better idea, and you can know how much of a time sink it is to actually implement something and try to get it working. But yeah, this is definitely something sort of to watch out for. It's not like, oh, there's this thing, I will just spend 2 hours, get this working, and then it's done. It's enormous amounts of time, right? There's a reason why these like massive teams of like 12 Google engineers are working on these kind of things. And it will be difficult to compete with this if you do not have this manpower and also, frankly, compute power, yeah? So just to give you an idea, maybe back to the previous one thing that they do say is that when they generate synthetic data, they're talking about hundreds of millions of theorems that they're synthetically generating with proofs. Yeah, so we're still at the point where we need insane amounts of data. And then to train this, whenever they say we used AlphaZero, this basically means they probably had a similar energy footprint to what it took for them to train AlphaZero on Go or chess or whatever. And if you read this, this was thousands of GPUs, yeah, which most of us do not have access to thousands of GPUs to just train for a day. You should know in advance if you care about the application or the method, which is very important, because if you care about the method, you want to basically write a machine learning paper or propose some machine learning approach, then you should sort of test it on a variety of problems, be open about the outcomes. If it's not working, sort of approach it differently and sort of be honest about what the method is doing. If you care about the application, you can sort of tweak your method as much as you like to this particular application, right? That's usually something that you shouldn't do. If you're if you're, I don't know, describing some kind of specific heuristic for integer linear programming, and then you just sort of just pick one data set and you really tailor to this one data set, and then it's doing very well on this one data set, that is not great research, right? Because this is probably not something that will generalize. If you have one particular application, then you can sort of tweak it to this as much as you like, right? But then this also just means that the method is maybe, yeah, you need to sort of give some caveats about how generally usable this method is. But if you get a result of it that you care about in mathematics, then that's great. You should, of course, be realistic in your expectations of what you can achieve. As I just said, many of these things, especially the sort of more advanced ones, require immense manpower. And you should also be aware of existing approaches, in particular beyond machine learning. So I didn't mention this during the individual results because I don't want to sort of point any fingers at any individual results. But if you've worked in combinatorial optimization, you might have seen some of these things and thought, but there's other ways of doing this that do not involve the neural network, and that is very true. So for example, if you're essentially doing discrete black box optimization, which some of the results in the first section were about, this has been very effectively done since the 60s. Yeah, so there's like many methods, and your first approach, if you're looking at a problem like this, should probably be use one of these methods. Do not immediately go to a machine learning approach unless you have a very good reason to do so, because it's definitely not the simpler approach. And then similar also in the second section, this basic idea of like gathering a bunch of data and sort of trying to extrapolate some connections. People have done for graph theory much before neural networks were really a thing, with like much more simple sort of statistical assumptions, and you can also sort of get very similar output out of this, right? If you look at the conjecture that they actually ended up proving, it doesn't use anything crazy in there. You can sort of just model this function using very basic statistical methods. All right, I'll leave it there.